Working with integrals. To integrate this, we remind ourselves of our trig antiderivatives. Find the antiderivative and evaluate. Simplify, and we get negative 2/3. Let's do the same integral, but go from 0 to pi over 2. Same antiderivative, different evaluation, and we get negative 1/3. Compare these two integrals. The net area under the curve from negative pi over 2 to pi over 2 is twice the net area from 0 to pi over 2. This observation is not a big surprise because our function is even, meaning f of negative x equals f of x. And an even function is symmetric about the y-axis. The area to the left of the y-axis is identical to the area to the right of the y-axis. And in general, if a function is even, then the net area from negative a to a is twice the net area from 0 to a. To use this property, your lower and upper bound must be the same distance from the origin. Let's look at a different integral. Remind ourselves of trig antiderivatives. Integrate. And evaluate. When we simplify, we get an answer of 0. The result is not a big surprise because the function is odd, meaning f of negative x equals negative f of x. When f of negative x equals negative f of x, your function is symmetric about the origin. With an odd function, the area to the left of the y-axis is the additive inverse of the area to the right of the y-axis. And in general, if you have an odd function, the net area from negative a to a is 0. It is important to note that the lower bound is the same distance from the origin as the upper bound. We will now apply what we have discovered. Let's evaluate this integral using knowledge of odd and even functions. Break this up into two integrals, and then examine the functions. X to the fourth is even. The cubic, x to the third, is odd. The lower bound is the same distance from the origin as the upper bound, so we can use our odd-even rules. Recognizing that we can use the odd and even rules cuts our work in half. Knowing that a function is odd or even can help with evaluating, but if you do not recognize that a function is odd or even, it often doesn't matter. You can evaluate the integral without that knowledge. Let's practice on one more problem. The lower bound is the same distance from the origin as the upper bound. Sine is an odd function, cosine is an even function. So again, our work is cut in half. Integrate the cosine function and evaluate. Then simplify. As mentioned before, you can evaluate the integral without knowledge of odd-even functions. Let's talk about average value. If we want to find the average value of 5 data points, We just add them up and divide by 5. What about the average value of a function, which can take on an infinite number of values on an interval? We know that height is area divided by width. Let's use that idea to find the average value of a function. Average value of a function from a to b is the net area under the curve divided by the length b minus a. So, average height is again area divided by width. Then we remind ourselves that net area is the antiderivative from the integral from a to b of f. Let's do an example. Use the definition to set up average value. Before trying to integrate, distribute the 2x. Then integrate and evaluate. So 1/3 is the average height of f on the interval from 0 to 1. The mean value theorem says that f will achieve its average height at some point on the interval. So let's find the point or points on the interval at which the function equals its average value. It looks like there are 2 places where the function achieves its average value. So we'll be expecting 2 answers. Set the function equal to 1/3 and solve for x. I multiply both sides by 3 and distribute the 6x. To solve this, notice that it is a quadratic equation. So put the equation in standard quadratic form and use the quadratic formula to find x. Simplify to get the exact values of x. Then estimate the approximate locations of x. The average value of f on the interval 0, 1 is 1/3, and f achieves that height when x is about 0.2 and about 0.8. Take care and have a great day.